with our basic objects in hand, we're now going to move on to the one key relationship among these objects and take our first foray into that relationship. We're going to come back to it later to fill in the rest of the details. Each of these objects provides some model of convergence or divergence, and the only question that matters is, does one of these objects fit into another one's model, the ideal location on the real line it sets up? We're going to indicate this with an arrow, and I just want to start with a very simple statement that should be fairly clear to understand intuitively once you see the objects. Does this notion of squeezing towards one from the right side, this 1 plus, which looks as such, does that fit into the ideal, the position on the line set out by this concept, this object of 1 plus minus? Well, that's the model set out. And the answer is yes, because, well, one is less restrictive than the other. The 1 plus minus is a bigger target, and the 1 plus fits inside it. In fact, that's the way we should always think about this relationship. We think of the blue object on the right hand of the arrow as the leader in the game, and the red one is the chaser, and I'll probably use that terminology throughout. The leader sets targets, squeezes closer and closer to some location, and the question is whether or not the chaser can squeeze enough to fit inside those. So the arrow is sort of a fits into or chases. The game is exactly a follow the leader game, or a Simon Says game, or dueling banjos, or whatever you prefer to call it. The leader sets the stage. Simon says, can you get this close to one? The chaser gets to try and catch up and see if he can. In this case, yes. Well, fine. Can you squeeze this close to one? Because these things keep squeezing closer and closer and closer. And the chaser gets to try and catch up. Yes, he can. Closer still? Closer still. This is the logical game that's played, the concept that's at play when we write this arrow. And notice that we haven't put any for alls, there exists epsilons or deltas on this, but the notion can already be explored at the very, very basic visual intuitive level. Let's reset these. Once you've played with it a bit, you quickly see what the situation is. The leader sets the stage. He can squeeze as far as he likes, and that's simply a for all statement. For each epsilon, no matter how small epsilon is, let the target squeeze. That's the for all epsilon greater than 0 for each epsilon greater than 0. What happens next? The chaser gets to try and catch up. Well, how do we measure the chaser? Well, we're just choosing conventional letters now. We all know they could be anything, but the convention is for small quantities, epsilon in the output and delta in the input. So the next line of the definition is, can the red guy squeeze far enough? Well, how far does he have to squeeze? He should be able to squeeze far enough, at least one delta. So let's let that run. So that, well, let's just express this fitting into in symbols. Well, if we name the variables in that top slice, that 1 plus, the picture tells us the inequality. Remember, we started with these pictures grown from the inequalities in the definition of limit, but the fact is, getting the concepts in the right order, the picture of what 1 plus looks like directly tells you the inequality, so you can actually work from the intuitive and visual to the symbolic. So we call the numbers in that red interval x, and you can quickly read it off the picture. X needs to be between 1 and 1 plus delta. What's supposed to happen? Well, each one of those points should also be fitting into the blue. And, well, the blue is also an inequality which you can draw directly from the picture. That same x should be able to drop down, all of them, and should lie between 1 minus epsilon and 1 plus epsilon, but not be equal to 1. This looks an awful lot like the definition of limit. We've never used the word limit. We don't want to use the word limit. And you might notice one other thing. It doesn't involve any functions. This is, I think, a key point. Every single bit of the logic of convergence and fitting into and limit, everything that we study in calculus at the basic level is already contained in this statement. We can view the statement. We can define the statement. We can even prove the statement in its pure form. No arithmetic necessary, no functions involved. Get all the key logic down, the for alls, that there exists, the ifs, the thens. See what everything means before things get complicated with functions. The advantage is, once you get this down, adding the tiny extra complication of functions logically is trivial. Now, of course, if you're actually going to write some proofs, that makes a lot of complicated algebra, but the logic need not be encumbered with the arithmetic and the functions. We can see the concepts in their pure form here. Of course, this relationship is not symmetric. 1 plus minus certainly does not fit into 1 plus. We could still write the definition as before. For it to fit in, no matter how far the leader squeezes, the chaser should be able to squeeze enough, to fit inside. But the thing we see, and we can see it, is certainly no matter what delta we choose, it's never going to fit inside that target because of the stuff hanging off to the left. Okay? Now, the statement is false. We can work through the refutation of if all there exists if we want to, but even if we don't, if we clear all this off, dequantify everything and get rid of the definition there, we can see and feel and understand conceptually what's going on here, and that visual understanding can tell us exactly what the definition says. We can put symbols on the concept instead of trying to extricate the concept from the symbols. The same relationship holds for things like infinity. I mean, positive infinity fits into positive negative infinity. Why? Well, no matter how far the leader squeezes, right? The chaser can squeeze enough to fit inside there. Okay, if the leader squeezes a bit more, the chaser can squeeze a bit more. If you wanted to prove this, the algebra would be easy. How would we actually write the definition? Well, again, apples and apples with the infinities and the convergent guys. The only difference is we're going to use m's and n's. Okay? How do we measure the leader? Capital M is the conventional choice. For each m greater than 0 says, let the leader squeeze as far as he likes. What should happen? Well, just like before, there should exist, we should let the chaser squeeze as far as he likes, which means there exists an n, so that, well, what happens? I'm going to always use x, I guess. Call the things in the red slice x, and you can read it off the picture. To be in the red slice means to be bigger than n. If x is bigger than n, if x is a red point, then it fits into the blue. So what does it mean for x to fit into the blue? Well, read it off the picture. X is either less than negative m or greater than m. And we have it. Before I leave this, I want to get to a slightly different case. I want to pose a question. This big old target 0 infinity, all the positive numbers, what would fit inside? Well, the answer is lots of things fit inside. 1 plus fits inside quite nicely, okay, without even squeezing anything. In fact, the target is constant, so there's no squeezing going on there. The chaser can squeeze as far as he likes to fit inside, but he doesn't have to. 0 plus fits inside. Well, 0 plus minus doesn't. Fine. Some things fit inside, some don't. In fact, even infinity fits inside, of course, not vice versa. The target doesn't squeeze, the infinity does. It fits inside, right? The point I want to make here is this open interval 0 to infinity is a very large target. What fits into it? Almost, well, a whole lot. Anything that doesn't have any negative or 0 quantity to it will fit inside. 1,000 plus, 10,000 plus, 0 plus, 1 plus minus, infinity even fits in. To say something, to make this statement, something fits into the interval 0 infinity, doesn't tell us much about that thing that fits in. This is what's literally going to be our picture of what indeterminacy means. If I tell you that something fits into 0 infinity, you can't tell me much about what it is. It might converge, it might be 2 plus, or 0 plus. It might diverge, it might be infinity. I can't tell, I can't determine. This is indeterminacy in its purest form. Okay? Again, indeterminacy, definitions, and proofs. We can see all these concepts before we deal with complicated functions or complicated algebra, and get something out of these. And that's a key selling point. With that, I'll leave the arrow relation alone, and we'll come back to this later, and it'll be quicker that time. All of the logic we've already seen. We just have to insert functions and arithmetic into the game.